Welcome, everyone. Today we're going to talk about space and time and the very large amount of time, covering a lot of space too, that ran from St. Augustine in the year 400 all the way up to the James Webb telescope today. And it's quite an interesting story. I'm Tom Sheahen, and today is March 29th, 2024. And I'm happy to be with you, and I hope that I can tell you some things that you will find interesting and worth learning. The James Webb telescope is the newest and best telescope there is. I'm going to tell you about, why it matters and how it's different from other ones. I'm going to then go into discussing the idea when you look out, way out in the telescope, you're looking out in space, but you're also looking back in time. And then I'll go into the insights that St. Augustine had long ago, about year 400 AD. Then we'll get a little bit on the matter of symmetry and how those determine the law of nature. And then finally, I'm going to talk about my own book called Every When, God, Symmetry, and Time. What I'm looking at here is a picture of a telescope. Not the kind of telescope you imagine, because you're not something you hold in your hand with an eyeglass or something. This telescope is a radio telescope, and it's known as the Very Large Array, and it sits out in the middle of the desert in Chile. So that's one example of a telescope. There are many other different kinds of telescopes in the radio range, the millimeter range, the microwave range, the infrared, and the visible. And all that you have probably thought about in the past is a telescope that sees in the visible. But what we're going to talk about today is a telescope that sees in the infrared. So again, a radio telescope, many of these form a very large array. And because they are linked together by computer, they combine to be one telescope and produce one image. And that's going to be important when we get to the James Webb telescope. In the James Webb telescope, it was launched on Christmas Day a couple of years ago, and it was placed out in space at something called the Lagrange point. It's a stable position where it'll stay there and not drift around. It's not the kind of thing where the orbit has to be corrected with a vernier rocket now and then. It just sits there, and it'll be there for a long time, as in millions of years. The distance from the Earth is 1.5 million kilometers. That's about 1 million miles out in space. When they put it up, it got out there fairly quickly, but they had to do some work on it for about 5 months to get it to work right. And the most important thing was to put up the sun shield, because this telescope doesn't like sunlight. It likes infrared light, and you do not want it, when you're trying to look out in the infrared out to space, you do not want your telescope mirror heated up by sunlight, and therefore you've got the shield from the sun. There are 38 pieces that form the mirror. As I just mentioned with the picture of the radio telescope, when you have many different components and you aim them just right, then they produce one image. And the one image produced from this very special mirror, that's what's shown in yellow there in the picture. The resolution is 0.07 arc seconds. Well, Galileo had about 1 arc minute, and he had a very good telescope in his day. But the quality of telescopes has just improved immensely as they've been ever better and better to control the mirrors, control the equipment, and so forth. So the first good images came back in the summer of 2022. And here's an example of one of them. Obviously, a galaxy casting out an awful lot of dust and gas and so forth. This is something you can see in the infrared, but not in the visible, because dust and gas doesn't show up very well in the visible range. The vision that this telescope has is better than even the Hubble telescope. And remember, the Hubble was put up about close to 30 years ago. And it gave him remarkably good views of outer space. But this one is even better. In the infrared, the spectral range is from 0.6 millimeters out to 28 millimeters. And I remind you that the range of the human eye is from 0.4 millimeters to 0.7 millimeters. That's also known as 400 nanometers to 700 nanometers, or 4,000 angstrom units to 7,000 angstrom units. So from 0.6 to 28 means that you do get red and orange colors as we would in the visible, but also it goes way out into the infrared to a very long distance of wavelength. Well, the instruments aboard this telescope complement each other. You have the complicated lens of the 38 panels that gives you a focused beam of light. I'm calling it light, but it's infrared light. And then the instruments take over from there, and they do different things. The different instruments see different things, and you can make them combine into a way that you get a better and better picture. The most important thing probably is that because you're looking out in the infrared, you can see cooler objects. So you can see gas and dust clouds that in the visible range, we sit here on Earth in the visible, and all we can do is infer that they must be there. But now you can actually see the dust and gas clouds. And you can also see exploding nebula. For example, here's how much better the vision is. Neptune, the planet. We sent the Voyager satellite out there to get close to Neptune in 1989. Then the Hubble sees Neptune with a bit of faint, fuzzy, not perfect focus, but that's as good as it can see it. And now the Webb there over on the right shows you that Neptune very clearly, and it even has a ring around it, which is visible in the infrared, but not in the visible range. So here's a comparison of Hubble versus Webb. Same thing out in space. That's as good as we had in the Hubble 30 years ago and with its vision. Now the James Webb telescope gives you much more sharp version. So that kind of tells you what we're dealing with here in terms of the quality of the images from the Webb telescope. This is an area in space where new stars are forming. That's a great big dust and gas cloud in front of us, and way in the background you see lots of stars. Those could be a jillion miles away, but what we're looking at is the star forming area in this sort of brownish seascape almost. But again, you see it with Webb, you don't see it in the visible. Here is an exploding star that is casting off gas and dust. Right near the center, the blue means it's pretty hot. Then as it moves out, it cools off and it's not quite as blue, and then cooler, cooler, cooler as you get further and further out to where it's just a faint orange and so forth. Again, an accomplishment of the Webb telescope. When you look back in space, I remind you that the speed of light is 3 times 10 to the 8th meters per second. That's 300 million meters per second. It's still a finite number. Sunlight takes 8 minutes to reach the Earth from the sun. But when we look at distant galaxies, we pay attention to something called the red shift. And light, we say, is red shifted from the visible range into the infrared. And in this way, you can tell how fast something is moving away from us. When you measure the red shift, you do so by looking at certain lines of the hydrogen atom or molecule. And you know they have to be at a certain point because you've measured it on Earth. But you look out in space and they're not in the right place anymore. They're shifted off in the direction of red, perhaps into the infrared, and that tells you that they're moving away at a certain velocity. So when you're talking about a nearby star, Alpha Centauri, something you know, Big Dipper stars, it's a negligible difference. They're still very much in the visible range. But when you're getting stars that are moving very, very fast at high speed, relative speed, that's when you get a large redshift. Now here is a view from the Webb that shows you a number of things, and you see some little streaky lines and all this kind of stuff. Sometimes there are things where you're looking at a galaxy and you can see it very clearly, but other galaxies aren't so clear, and you wonder why aren't the other ones clear? And the answer is because the light coming from them is bent by the gravity of other objects in between that source and us. And that gives you a distorted picture. When we look at this picture, there's several bright stars that are probably in the foreground, but what we're looking at is the background stuff. And that's where we see all these peculiar shapes of images that are caused by gravitational lensing. Again, an accomplishment of the Webb telescope that we've never had before. When you look back in time and space, you have to remember the theory of relativity. And I remind you that it's not just the old slogan E equals mc squared, but rather the fact that time and space are interchangeable. They're related symmetrically, and physics describes the universe as a four-dimensional thing. On the right here, I've shown a picture of a Minkowski diagram, which is a way of representing the fact that space and time are interchangeable. Variables x, y, z, and the time variable is called I times c, the speed of light, times t. The time variable in the equations of physics behaves just like a spatial variable. And that's important for grasping distant objects and far away and long ago objects too. So now we talk about St. Augustine a little bit. He was a philosopher back around the year 400, and he was the first person to realize that God created space and time together. Space and time are a unit. They come together. That was the beginning. When God created time, then and only then could the clock start. There's no meaning to the word before until after time was created. And St. Augustine himself pointed out how silly it was to ask questions about what was God doing before he created the earth, created the universe. And the answer is there was no before until God created. Well, over the centuries, people forgot about what Augustine had discovered. And it was only 1,000 years later that we began to develop science in the Renaissance period. Names like Robert Grosseteste, Roger Bacon, and so forth are early scientists from the early Renaissance. And late Renaissance, the 17th century, Isaac Newton came up with classical mechanics. But in classical mechanics, you treat time as totally different from space, and time is just there. It's linear, it's absolute, it runs forever, both backward and forward. So that was the nature of physics from about the 17th century through the 19th century. Well, in the 20th century, Einstein came along and he rediscovered what Augustine had said in the first place. And general relativity relates time and space in a symmetrical way where they are interchangeable in the equations. So in modern physics, we've learned a number of things based on our knowledge of both gravity and quantum mechanics as well. We've found that every universe must have had a beginning. No universe can possibly go back forever. The time doesn't go back forever. There's a starting point. This is something that Father Spitzer has written about considerably. Three scientists named Bordy, Vilenkin, and Guth showed that proof in a paper in Physical Review Letters in 2003. And it's been very clear to all investigators that a universe has a beginning, including our universe, probably the only universe. So, in my book, which is entitled Every When, God, Symmetry, and Time, I begin with Augustine's insight about time and space. And the fact that creation of space and time was the beginning, I go from there to talk about what happened beyond that and what is happening all the time anyway. Certain properties of God: omnipotent, omniscient, and omnipresent. Well, omnipresent means God is present to all places and all time. So the word every when is a parallel to the word everywhere. Now, we know what everywhere means, but none of us have ever heard of the word every when. And the reason is we humans can't comprehend all time in a united way. We say all at once. No, that isn't it. No. God can be present to all time. We humans cannot grasp that at all. But what God did to begin his creation, he thought up certain symmetry principles. And from those symmetry principles came the laws of physics, all the particles that we know in nuclear science and atoms, molecules, etc. Everything created derives from these symmetry principles. From simple particles assembled into more complex form, and pretty soon we have molecules, then we have complex chemicals, then we have, all the way up to sentient life and ultimately to intelligent life or human beings. The way creation followed upon God's beginning is that God is the first cause of everything. From the symmetry principles, which, as I said, God thought up, come the law of nature. Whether it's strings, quarks, particles, anything, all the way up to intelligent life, it is God's transcendence that enables it all to take place in the mind of God. And I point out in particular that God had a goal in mind all along, and it doesn't matter how long it takes when you're simply present to all time. And an all-loving God was able to create a being capable of loving God in return. That's humans. That was probably the reason that there is something instead of nothing. Physicists have puzzled over that question for a long time. But the reason is because God wanted there to be a creature capable of loving God in return. Well, humans can't comprehend everything the way God does. Human thought, culture, and language get in the way. Every author has additional limitations in background, location, specialization. I'm a physicist. I'm not a theologian. So my ability to write on this subject is very limited. But there are possibilities for others to advance our knowledge to a higher degree. Thinking in higher dimensions expands your mind and gives you a window onto something that is beyond what you would normally comprehend. When you combine mathematics with other means of expression, you can advance a lot further too. There are unlimited opportunities. And the important thing to remember is that what God created is not bound by human intelligence. We're limited. God isn't. So, in conclusion, the James Webb Telescope is the most advanced telescope ever. It enables us to see objects that are much cooler than stars. We can see back, way back, to nearly the origin of the universe, only 200 million years after the Big Bang. At that time in the universe's history, condensation into stars and galaxies had barely started. Now, the essential contribution of St. Augustine was that God created both space and time together. That's fundamental. He lived in Carthage, and that was the contribution of Carthage to this insight into the universe. And it is more important now than it ever was before. The importance of symmetry principles, which God thought up, is that they point to the astonishing intelligence and creativity of God. So that's my story, and I hope that you will give it some thought. I hope you will appreciate from this magnificent telescope how much we know, but at the same time, how little we know of everything about God. We're making progress. We are advancing science, but we've still got a long way to go. And on that way, the travel, faith and science make that journey together. And that is a very important thing to remember. Thank you very much.